Let's take the material of the last video and apply it to column vectors. So we remind ourselves of what we were saying in the last video. Suppose we have a basis of a vector space, a finite basis of n vectors. Then any vector in the vector space can be uniquely written in terms of these basis vectors. But that means that any vector in the vector space can essentially be thought of as a list of numbers. If we know what the basis vectors are, then all we need to know to identify this vector is what the first basis vector is being multiplied by, what the second basis vector is being multiplied by, and so on. And a list of numbers can be thought of as a column vector. So however complicated these vectors look, and however complicated the vector space for which this is a basis looks, the elements of that vector space can be stored in a very simple way as lists of numbers. And now let's apply this insight to the case where our vectors are already column vectors. Let's look at R2, and we'll take as our standard basis 1, 0, 0, 1. And we'll look at some specific vector, let's say 3, -4. 3, -4 is 3 times the first basis vector plus -4 times the second basis vector, and that therefore can be stored if we record the coefficients as 3, -4. So this must seem like a kind of inane observation that the vector 3, -4 can be stored as the vector 3, -4. Well, yes, it can. I mean, what's that supposed to get us? But let's look at the same space with a different basis, the basis 3, 0, and the basis 0, -4. And let's look at the same vector, 3, -4. It can be uniquely represented in terms of this basis. And now, when we store it as a column vector, we get something else. The coefficients are 1 and 1. So this column vector can be stored, if we're given this basis, as a different column vector. But why? I mean, why do we want to do something like that? Let's go back to the introductory example we gave. Where we have an ellipse, and we'd like to talk about this ellipse, but unfortunately, the major axis of the ellipse is there, and we only know how to write the equations of ellipses when their major axis is parallel to either the x-axis or the y-axis. And we said, well, one way we could resolve that is to simply redraw the axes. If we draw a new x-axis and a new y-axis, then this ellipse is now in standard form. Okay. Consider a point on the ellipse. This point has an x coordinate and a y coordinate, and the x and the y coordinate are determined in terms of the x and the y axis. We go along the x-axis by this amount. That's the x coordinate. We go up the y-axis by this amount. That's the y coordinate. Maybe this is the point 1, 3. When we redrew our axes, we also changed how this point is represented. represented. This is a new number, and this is a new number. In terms of this new x and y coordinate, this point is maybe 4, 2. So is it 1, 3 or 4, 2? There's no objective answer to that question. It depends on where we've chosen to put the axes. So this provides the tools to allow us to do that. Is this the vector 3, -4, or 1, 1? There's no objective answer to that. It depends on what we're using as a basis. If our basis is the standard basis, it's 3, -4. If we want to use this non-standard basis, it becomes 1, 1. If we want to use our regular x and y coordinates, this is 1, 3. If we want to use these redrawn x coordinates, it's 4, 2. Of course, we need now to get our notation straight. This runs the risk of being terribly confusing if you've got the same point represented in 2 different ways, or if we've got the same vector represented in 2 different ways.